All right, the last periodic table trend we're going to look at is chemical reactivity. So by the end of this, you will be able to identify the reactivity trend, rank the atoms based on that reactivity trend, and predict the reactivity based on the location the atom is on the periodic table. Okay, so first of all, what is reactivity? Reactivity is how willing an element is to have a chemical reaction with other elements. Essentially, it's reacting by gaining or losing electrons. So the easier it is for it to gain or lose those electrons, the more reactive the element is. And there's actually two different trends on the periodic table because those metals and nonmetals behave differently. So if you remember, metals lose electrons. So the more easily the metal can lose the electron, the more reactive it is. And nonmetals gain electrons. So the more easily it gains those electrons, the more reactive it is. And this is, that's kind of review from the ions lesson, is whether they're gaining or losing electrons. So we have to look at the two different trends, and we're going to look at them across the periods and across or down or up the groups. Okay, so we're going to start with metals. And remember, metals react by losing electrons. So the more easily it loses the electron, the more reactive it is. So if we compare lithium and beryllium, which are right here on the periodic table, right next to each other, what we find is that there are fewer protons in lithium. So if it only has 3 protons versus beryllium having 4 protons, then the attraction isn't as strong in lithium. So it's going to more easily lose this electron. So lithium is more reactive. And so that's where we get this trend that going from right to left across the periods becomes more reactive for metals. Looking at metal reactivity down the group, so if we look at lithium and cesium, so lithium's here and cesium is way down here, okay, we see in this Bohr model for cesium, I didn't draw all the electrons, it just would be too messy, but we see that there are more energy levels between this electron and its 55 protons. So even though there's more protons, this huge distance between the electron means that this one will be easier to lose. So cesium is more reactive than lithium, and so our trend goes from top to bottom down the group. So lithium is less reactive than cesium. Okay. So now we move on to nonmetals. Nonmetals react by gaining electrons. So the more easy it is to gain the electron, the more reactive the element is. And that is opposite from our nonmetals. So we end up with dual trends within the periodic table. So if we compare oxygen and fluorine, so oxygen is approximately here on the periodic table, and fluorine is right next to it. Okay, we have to look at that, the protons and how strong that attraction is. So in fluorine, there's actually more protons, so it's going to attract to gain electrons easier because it has more protons than oxygen does. So oxygen only has 8, so it's not going to attract those electrons quite as strongly as fluorine. So our trend ends up being, as we go from left to right in the nonmetals, we get more reactive elements. That was the wrong color to choose. Okay, so as we go that way. And then when we're going up the group, we get more reactive elements. And let's look at why that is. So again, the more strongly it attracts the electrons, the easier it is to gain them. So in fluorine, this distance between the outermost shell and the protons is less than this distance in iodine. So fluorine is going to actually attract to gain electrons more easily. Electrons more easily. So because that distance is smaller, the attraction for the positive proton to the negative electron is stronger. So fluorine, which is right here, and iodine, which is right here. So fluorine's up here. It is more reactive, so our trend actually goes up the group. Okay, so we are going to, on your periodic table, I recommend, it's kind of a lot to draw in, but the first thing I would do, and you should have already done this for our ions, is make sure that your stair step is here. And I actually had you color in the elements that were metalloids, that separated right over here is metals and over here is nonmetals. Okay. So the first thing you have to do when you're asked which one, we're going to order these from least to most reactive. So we first have to ask, well, are they metals or are they nonmetals? Calcium, beryllium, barium, magnesium, strontium, those are all in this column, so they are metals. And so the trend is least reactive on top, most reactive on bottom. So we're going to say beryllium is least reactive, then magnesium, then calcium, strontium, and finally barium. So this is least reactive to most reactive. Okay. And again, that is because we have more electron shells, and so the electrons will more easily be lost from barium because it doesn't have as strong of an attraction to the nucleus. So our next one is sodium, aluminum, and magnesium. So sodium, aluminum, and magnesium is over here. Again, we have to ask, well, are they metals or nonmetals? Well, they are metals, so we have to follow these arrows here. And so our least reactive is going to be aluminum, and then magnesium, and then, and then sodium. So this is least to most reactive. And that is because they have, aluminum has more protons than sodium, and so sodium sodium has fewer protons, so it will more easily lose that electron. I had to make sure I was saying it the straight way. Okay, so then the last two examples over here, so we have to ask, well, is carbon, oxygen, nitrogen metals or nonmetals? And we see over here that they are nonmetals. So then our least reactive is on the left, and we go to our most reactive on the right. So it goes carbon, nitrogen, oxygen is least to most reactive. Okay, and review, that is because of the number of protons they have. And then it's arsenic. Arsenic, nitrogen, and phosphorus are also nonmetals, and the trend is from least to most, from bottom to top. So arsenic, phosphorus, nitrogen is our least to most reactive, and that is because our number of energy shells. Okay, and then this one, I just have the key for all of those written out for you.